people do the other thing, which is, I don't know, I timed it, I changed something, and I saw if it got faster. That doesn't tell us anything.
Hey folks, and welcome to Marco Codes. This is the first episode in a series where we're going to dissect a solution to the 1 billion row challenge in Java. Last year, someone posted a challenge online where they said, hey, we have a text file with a 1 billion text rows, and these rows contain temperature measurements. So you just have like a city name and then a semicolon, and you have a double value of the temperature. And the challenge was, how fast can you read in that file containing 1 billion rows? It's about roughly 12 to 13 gigabytes large. Do it in Java as fast as possible. And there were many different submissions. The idiomatic Java codes took, I think, roughly a couple of minutes to complete. The fastest solution was under a second, to read in the file, not just read in the file, but also perform a couple of calculations like the minimum value, the average, the maximum value. And what I wanted to do is, I've always been thinking that Java developers kind of have a wacky understanding of performance. So whenever your application then just gets a dozen requests per second, you think, oh, I need to immediately scale my Kubernetes cluster and think about back pressure and those sort of things. And what I really wanted to do is I wanted to go through the challenge, even though it's a bit synthetic, see how I would tackle it from a performance perspective and how we could actually bridge everything I've learned from that challenge to the real world. I possibly couldn't do any of that all by myself, which is why I got some help. Casey, hi, hope you're there.
I am here. Hey, Marco, it's good to see you again.
It's good. It's great to see you again as well. So in case you don't know Casey, I don't even know if I have to introduce you anymore. But even though you say otherwise, I think you know a shit ton about performance, much more than I do. You also wrote a performance web programming course, which I've been a member of, and I would recommend you to check out. I'm going to link it down below. And you can also learn how to build a video game from scratch on your YouTube channel, Molly Rocket. But nevertheless, what I wanted to do with you, Casey, is I already spent some time working through the 1 billion row challenge, not the entire thing, but just like the first step, so to speak. I would love to have you as sort of a reviewer, which means we're going to go through my code that I wrote, bounce off some thoughts that I had, ask you questions because you know your stuff when it comes to, let's say, lower level programming, and not the Java stuff I'm usually doing. And we're just going to work through the code. You can scold me if I did something wrong. What do you think? Well, how does it sound?
Yeah, it sounds great. I'm also looking forward to it because I don't really do any programming in Java myself. I'm not really very aware of how hard it, like, I'm going to ask you for all these things. I'm going to be like, can we look at this? Can we look at that? Right? And I'm interested to see, it'll be like, well, I don't know. Let me go see if we can do that. Right? I want to know, I'm looking forward to the education in what I can and can't get access to easily. Things that I might have taken for granted when I'm programming in a language that's maybe, has more people looking at it for performance, right? But my understanding is Java is pretty capable of high performance code these days. They've done a lot of work on it over the years, so I'm expecting that we can get pretty far down that road. So we'll see.
That would be super cool. And by the way, I think that we should all be learning from each other. I mean, in this case, I'm going to be learning from you. But what I mean is that Java developers should just get out of their box or out of their silo and learn other stuff, other languages and whatnot. Let's see what we all can learn about performance through this series. All right, then I would just jump in and jump straight into code. Let's check it out. So what I did is, and what you can see here, just briefly what you're looking at. Maybe I should show you the text file again. So I have that text file with the 1 billion rows, and that's what it looks like, right? Measurements txt, as I said before, you have a city like Beijing, you have a double value, and that's about it. So far, I guess, nothing too special. Okay. With the exception that it's in UTF-8. So, but yeah, that's just a tiny detail. Just a simple, not an exception, but just a normal UTF-8 file.
Okay. And I assume that by that you mean we will see some things in here that are actually using the UTF-8. Like, for example, is there some, kanji? Like, is Tokyo written as Tokyo as opposed to the Ramaji or
that actually I don't know, but I don't know
Okay.
with these letters, Suwalki and whatever, where they come from.
Okay.
But yeah,
Some of
yeah.
those might not be in the Latin or what character set or something. Yeah.
Exactly. Yeah. Right. Then what I did is, and by the way, I'll also what I usually tend to do is when I do these proof of concepts, I create a project, I create several versions of Java classes. In that case, I just call them blah. So it's just blah 1, blah 2. This is my second try.
Got it. Got it. Yes.
Nothing is cleaned up. Nothing is optimized yet. It's just a rough cut, so to speak. I didn't want to pre-polish it, whatever. It's just my raw thought process in that case.
A good process. You never want to spend time polishing something if you're not sure it's right, right? So, yeah.
Right, yeah. So let me just walk you briefly through what I thought, how would actually tackle it. When I looked at the text file, I thought, well, I have 16 cores or whatever. It would be nice if we could just at the beginning go ahead, reading the file, not just sequentially, but start with parallelism at the beginning, which means I'm going to split the file into, let's say, 16 different sections, so to speak, work them off in parallel. And then at the end of the day, this is stuff which I haven't done yet. We have to do the calculations, and then we have to merge the calculations back together at the end to come to the right solution. But I thought, hey, I'm just going to access the file, split it up, read it in parallel, work it off in parallel, and hopefully merge the results at the end and live happily ever after, right? I have a method where I just say, hey, give me the current file size, where I'm going to check out, hey, how many bytes does my file have? I wanted to basically divide the file size with the number of threads. Number of threads, as I said, is the number of processes I have currently available. I don't know, that seemed like a default choice, kind of. As a basic starting point, would you say that is okay? Would you start with something else?
Yeah, I mean, there's, I guess, I'm assuming that we're going to do many of these videos so that I can just sort of go on tangents as necessary, because the point is to kind of put as much educational information out there as possible. So I'm not going to try and restrict myself to only talking about things that I think would have an impact. So typically speaking, what we're looking at when we're thinking about dividing something up among cores in a computer is we want to think about what we're having those cores doing and what resources of the core we're going to use. So the only real concerns that you have when targeting processors is inside the CPU, right? There's kind of two different types or ways that it thinks about how threads are run. There's actually like physical cores of the processor, and each one of those does independent work, right? But then each processor can also potentially do multiple threads at once. That's what you call like hyper-threading, or I think AMD sometimes calls it simultaneous multi-threading, right? They have different words for what it is, but it's just the idea that you're going to have one core handle multiple threads at a time.
Right.
And for people who might not understand what that means, because, we think of threads, well, of course, that's what multitasking is. It's having a bunch of threads run at a time. Well, the operating system is the thing that's keeping track of all of your threads, and you could have thousands of those, right? But the CPU is only working on a subset of those threads at any given time, and the operating system is like swapping them in and out, right? It's like putting in one thread to run for a little while. When that thread's run, it'll swap that out and let another thread run for a little while. And so there's kind of two layers there. There's the threads that the operating system is switching between, and then there's the threads that a CPU has been given by the operating system and that it's switching between. And these two operations are very different. Switching out an entire thread at the operating system level, so handing a new one to the CPU and coming back, is a more heavyweight operation. It costs more to do that. When a CPU core has multiple threads, that's very fine-grained. It's actually basically feeding two threads or more. Some processors have like 4 threads. GPUs do this times 100, right? They do tons of threads. That's a separate model, but yeah. So on CPUs, you have 2 or you have 4 potentially. It's going to be feeding instructions from those different threads into the CPU, like essentially simultaneously. Like it's basically just looking at whoever has work available. It's just like, jamming it down into the CPU as fast as it can. And so that's not a heavyweight operation. It's doing that literally at the instruction or micro op level, right? And so the only thing that we kind of have to be aware of when we do something like let's run on all available processors is we need to know whether that means all available actual cores or whether that means all like logical cores, meaning, if a core can do 2, right? Are we then going to double up? Are all of our cores getting 2x the work?
I think actually we're going to double up, but I'll have to double check.
Almost certainly you will, because that almost certainly is going to return the logical core count, because getting the physical core count is very different. So there's that. That's thing one. And the reason that we might care about that is because essentially when you have 2 threads running on one core, that core does not become more powerful. It still only has the same amount of resources as it did before. So for example, it still has the same amount of cache on that core. It doesn't get more cache just because it's running 2 threads. So sometimes, right, when you're really, because, I don't know how deep we're going to go on this. Sometimes when you're really looking at performance very carefully, you need to consider, do I want to have the amount of cache that I have available to my threads? So does that make sense?
It does make sense.
Yeah,
it absolutely does. It absolutely does. And I think we need to go down into that specific topic in a future episode. I would love to go dig deeper, but that was a very good explanation.
Okay, so there we go. So we'll talk about that later if we need to. The other thing you need to think about here is that when you're looking at how many processors that you're going to run on, you also might be running on a laptop. That's not a case we necessarily have to care about as much, because I think this challenge was like you submit it to a server and they run it or something like that. So we're not maybe as concerned about that here, but normally you have to think about, okay, if I run something on every processor, on say Intel laptops now, the cores are heterogeneous, right? This is also the same on Macs. You have certain cores that have much more powerful capabilities than other cores. So when you target all processors, you have to be aware in your own head that that means you may be getting a completely heterogeneous group of processors, some of which will run very fast, some of which might run much slower. And so if you're not taking that into account and you're doing something where, say, the slowest person will kind of dictate the overall speed of the algorithm, then you may really harm your performance, because you'll be sitting around waiting for the low performance cores to finish something that the high performance cores can do much faster.
Which I think is a default, to be honest. And I think not many Java developers are even aware of how to reason about that topic. But also, let's get into it. Let's get into it at some point.
Yes. So anyway, so those are the things to think about there, and we'll cover them later if we have to, but that's what we're looking at. Okay.
Very cool. So we were here, we had the file size, we had the chunk size. So let's say I have a specific chunk size. I thought, hey, we're going to just split the file into sections. Sections is really just a Java class where I say, hey, a specific start position, a specific end position of the file. And then the thing is, when let's just say I just divide this file by, I don't know, 10, 16, it could be that I'm actually splitting it right here in between, in a line, because I don't even know where I'm splitting it. I just have a start and end position. I could end up anywhere. So the next step would have been to say, hey, I try to split it here, and then I need to read in a couple of bytes still to figure out, hey, when does the next new line character come? So I actually adjust the thing for a new line, which is, let me just scroll up a tiny bit again, which I hopefully do somewhere in here. So yes, split sections. Let me just check it out. I have a split section where essentially this the code I was just talking about, just for the threads. I try to figure out the right start and end position for a section. And for every section, essentially, I try to find the next line start. Well, go ahead. For whatever reason, I just put here, I'm allocating a byte buffer with 8,192, well, whatever. And I'm just reading through and trying to figure out, hey, do we have a new line character? And then this is the real end position where the section should stop. That's
probably fine. One of the things that the very first thing we're going to do at the end of this episode is take a quick look to see like what time we're spending where. While there might be some hidden gotchas in here, ordinarily because each one of these threads, of which, like you said, there's probably only like 16 or so of on your machine or whatever, we're going to be doing this operation so infrequently compared to everything else, we shouldn't probably have to worry too much about how it's being done. Now, obviously, like if we want to get down to every last little cycle or something, sure, but I'm not imagining we have to worry about it too much. So I won't, because otherwise I'd like go through it, explain to me what dot flip does, and explain to me right. And why are we allocating memory here? Like, can we have done that up front in one like? So there's things we would want to look at, but like, do we really care about this? We don't know that we do yet. So I just hold off on that. You know, basically doing the right thing, meaning that's what we do want to do.
Okay.
Right?
Okay. Cool.
Yeah.
Cool.
Yeah.
All right. Okay. So then we just have just getting back to here, right? Find X line start. We have the new file sections, which is great. Cool. Then once I have a list of sections, essentially, what's happening is I have my, let's say again, 16 threads. I create these 16 threads, and these 16 threads do nothing else, but they run one method, which is called process large section. I start the threads, I join them, which means I wait until all of them are finished, and that's essentially all of that that's happening. And by the way, what I'm doing at the moment, I can just quickly run my program here on my machine. I think at the moment it's going to take us 5-6 seconds to. Oh, well, that was 8 seconds, and I'm going to rerun it probably a bit faster. But a couple of seconds to just read through the file and just read through it once. But we'll talk about that a tiny bit later again.
So that 4 seconds there that we're observing right here, that's just to do like just for the threads to kind of go through and see what's going on.
It's basically for all the threads to read every byte of the file and
but not do the summing.
Exactly, not do the summing. No, nothing else.
You're timing it separately there, so that 2 milliseconds to split into chunks.
Yep.
So that's again, 2 milliseconds it depends on whether we think that's good or bad, but it's not. It's not like something we would be paying attention to now, right? Just as I surmised, right? It's not 2 milliseconds compared to the 4 seconds. We're not going to care about that for a while, probably.
Exactly. So So I'm happy with the cutting it up into chunks. With the rest, we'll have to take a look at. All right, process large section. So what's going to happen in processing a large section? I'm just going to memory map the sections that I have. File to RAM and let the operating system do it. That's what I can do here with this map by buffer. And then I noticed, well, in Java, and you need to correct me if I'm wrong, I can only map sections up to 2 gigabytes, which probably somehow has to do with I don't know, some indices being int only, and then so I could only do 2 gigabytes at a time. And if you try to map more, you'll actually get an exception at runtime.
Interesting. Okay.
That's why the problem is I have a process large section which actually splits it into subsections, but only, or into chunks, which I call them, but only if the section was bigger than 2 gigabytes, which it wouldn't be actually if I ran it now with just 16 cores, because the file itself is 13 gigabytes or whatever large. Still, the code is in here.
Okay. Yeah, that's all right. Yeah, I mean,
and
that's an unfortunate limitation, and kind of strange because, I mean, I think a lot of the environments where you'd be running Java, they are capable of doing full 64-bit file mapping. Like, they don't have a 32-bit limitation, or in this case, a signed 32-bit limitation on file mapping. So that's odd and somewhat concerning. Not that I'm a huge proponent of memory mapped files. Like, there's a lot of ways we can get around that. So I don't think that's going to cause any kind of huge problem for us. But, like, that's odd. Hey, Java people, like, what's going on there? I'm imagining this is like some kind of a cross-platform conceit where it's like, well, we have to be able to run on 32-bit Windows or something, right? And or 32-bit Linux distribute. I don't know. But that's weird. But continue.
Yeah, it is. And I think there's now with the new native API, it actually lets us it lets us map more chunks. But in any case, that is much more advanced, and we can look into it later. But what I wanted to ask you actually is, I was just thinking of memory map files, just like because I thought, hey, it sounds reasonable.
Right.
But is that the way I should have gone? And you just mentioned there would have been other ways also. So
Yeah. The problem that you have with memory mapped files is, at least in my experience, they're very unpredictable. So on some operating systems, on some machines, on some drives, right, you will get good, like you may be able to get the best performance for doing a sequential read set like this on memory mapped files, maybe. On other times, and in fact, I showed this on the machine that I use for the class that you mentioned that I do for performance-aware programming. On the machine that I do the testing on for that one, we actually did a section kind of on like memory map files versus buffers. And on that machine, memory map files were not faster, right?
Right.
And there are a lot of reasons for that. If you think about what has to happen with a memory mapped file, what's really going on there is the operating system kind of has to guess about what you're going to do. Because in the crudest version of a memory mapped file, really all that the operating system would do is it would just say, okay, I'm taking, we don't have to go into too much detail about how virtual memory works, but I'm taking this large swath of address space, just address space, not actual memory, address space. And I'm just going to say that big chunk, the size of the file, let's say, is reserved. And we're not going to actually do anything with it. So there's nothing, it's not actually mapped to any physical memory yet. We're just going to say it's reserved. And then when the program that asked for this goes and tries to read or write from one of those, from like a page in that address range, it's going to fault. It's gonna be a page that's mapped to some kind of a faulting address, right? And the operating system is gonna wake up at that point. Like you're running, that person's gonna wake up and go, oh, someone faulted. Oh, they faulted inside a region that I said was mapped to a file. Let me go read out that page and put it there and then resume that thread. Now in the naive implementation, with like 4K pages, and if it only just did what I just said, you're going to be page faulting and going back to the operating system on every 4K that you read, right? Which would be absolutely catastrophic for performance because there's so much overhead there all of a sudden. Now, modern operating systems are going to try to do better than that. They're going to see where you fault. They're going to try to read ahead. They might queue some speculative reads. There's all sorts of things they could do to try to make that faster. But whether or not they have managed to do so, right, is largely dependent on whether their guesses match what you're actually doing, et cetera, et cetera. So a lot of times in scenarios where you really care about I/O, you can beat the operating system by actually having some kind of an async I/O going in flight while you are processing. So like while you're doing your parsing for some chunk of these city names, the stuff that's in this billion line file or whatever, while you're doing the parsing of that, you before that have kicked off to the OS, hey, read me the next 64K of this thing or whatever, right? And so it can overlap that if it has more async I/O capabilities. And so sometimes what you'll see is the winning strategy might be something more like, hey, I use 15 of the 16 threads from my worker threads, and one thread is just a kernel thread that's sitting there servicing an I/O ring, right? Where we're pushing stuff on the I/O ring, it's pulling stuff off the I/O ring, getting those queued up, and we're all just working in perfect harmony, and there's no OS changes, no threads, getting halted and waking up. So it is true that like memory mapped files are just very hard to predict. And one of the things we will probably have to do, maybe a little further on in this series, is take a look to see if you're actually getting acceptable performance from these memory mapped files or if they're actually just slowing you down. So that'll be something that we'll do later.
Right, great point. Okay, cool. So then for now, let's imagine we have a memory map file and we're down to processing chunks. Processing chunks essentially means we have a lot of lines where we have a city name, semicolon, and we have a double value. So what I'm doing just now is essentially I have my map byte buffer in Java, and I'm just literally going through every byte. I'm just reading in every byte of the file. And I'm trying to figure out, hey, what part of the file here is my city? What is my double value? And then, obviously also transforming them into a Java string or into a Java double, for example. And then the first thing which I noticed is that in UTF-8, one character can have, I think, between 2 and 4 bytes. So the way I try to tackle it is essentially I'm just going through every line. I try to just proceed through a line, and I think you can see this, what I'm highlighting, right? I try to find, so I mark when I'm here at the beginning of the line, I go through it until I find a semicolon. When I find a semicolon, I understand that everything between my last mark and the semicolon is essentially the city name. So that's what I'm doing here, where I just, whenever I hit a semicolon, I read everything in before the semicolon, and that is my city. And then I go ahead after the semicolon, everything that comes afterwards until the end of line is essentially my temperature. And as you can, so what you can see here is I commented out a couple of lines because. So I have my bytes, which is fine. And then when I start obviously trying to convert them into a Java string or into a double, which by default, you actually go through a string and then pass a double value out of it.
Right.
What you will then see is obviously that the time will explode. And
really?
I can just uncomment it and I will just quickly show you what's going to happen. Let me just briefly see. Just for parsing that and doing these 2 parses. So we're parsing the temperatures as bytes and we're parsing the city. And I think it's actually, so 15 seconds. So it's another, let's say 7 or 8 seconds added to it.
Well, can you comment those out now and run it one more time?
Yeah, sure, yeah. With a zoom size of 175%.
It's hard to see. I know, yeah.
It's hard to see. So let's see what happens.
The pains of streaming.
Yeah, 4 seconds, roughly.
Okay, so the 4 seconds, because the first time, correct me if I'm wrong, but the first time when we ran the previous version that was 4 seconds was not a memory mapped file. And now this one is 4 seconds for the memory mapped file.
It was always a memory map file.
Okay, so even in the previous version, that was memory mapped as well. It wasn't doing reads of chunks. Okay.
Yep.
Just wanted to make sure I knew which one we were looking at. Okay.
Yes. Yeah.
So it's 4 seconds to do the memory mapped file version, and then it goes up to 15 seconds if you just do the double, not the other one. I'm just curious again.
Yeah, sure.
I'm just getting my bearings here on how.
Yep. Sure.
It's to what extent it's suffering.
And then it goes even further because I already tried 12 seconds. So actually it's the double parsing which is basically which is screwing us up.
All right.
And I have to admit I had a look at some of the solutions and they all pass the double manually. They don't go through a string.
Well, just that there alone. Now, again, I'm not that familiar with Java, so one thing that I couldn't say, for example, is we're looking at what's going on here, and I don't know how much of the work that's happening here could get optimized out if you don't actually parse the characters that are used. So, because I'm not familiar with Java, its compilers or any of that sort of stuff, I'm just saying. But the fact that we're not parsing the double and we're saving that much time is a bit odd, right? So, it's like kind of a little weird. But anyway, one nice thing that we have going for us is, at least as far as the current city parse part, we don't even need that, right? Because the mandate here is that we sum all these things together, right?
We do, yeah.
And so we can just use the raw UTF-8 bytes as our thing that we're summing. We don't, because they're going to match, right?
Okay. Let me just write that down as use the raw UTF-8 byte, right? True, yeah.
So that way, because if you think about what happens, let's say we do need to convert them to UTF-8 because we have to do like a sort at the end that's going to be like in some way, like the sort needs to be UTF-8 sensitive in some way. Like I don't know if that's true, but let's say that is true.
Well, we need to, true, yeah.
Like let's say that's true. I don't know. We haven't looked at that yet, but let's say that was true. We still wouldn't want to convert to UTF-8 here. Why? Because we know that we're going to see the same city multiple times. That's the whole point of this challenge, right? Is that we're supposed to be merging duplicates.
Right.
So there's really no need for us to parse these names every time we see it. We can just use the raw UTF-8, use that as our key for when we're doing our summing, into our map or whatever we're doing. Probably want a hash table, right? Looks like you've got one there. We're going to use that as our key, and then our sums will all sum properly at the very end, only once we've done all of the work. Then we can just parse each name once, because they've already been effectively deduplicated by our hash at that point, right? So that would save us work if it turns out that parsing UTF-8 is expensive. Does that make sense?
It does make sense.
Okay.
And by the way, just one more thing. I try to play with hash maps also, and to put them in here. And again, there is quite a performance penalty if you try to do that. And then I also saw that some of the solutions they built custom-made hash maps, blah blah. Yeah. It gets a bit fiddly.
I'm sure we will look at that stuff. This is always, I think this is a great exercise for these reasons. Like, all of these things are things that I am well used to, right? And I think people really underappreciate just how bad the default ways of programming usually are. They think that they're fine, or that they've been handled by experts in such a way that you couldn't possibly do better, or things like, it's like, actually, in a lot of languages, in a lot of cases, whatever the idiomatic thing is one of the worst ways to do it. It's actually really not good. It's very low performance. And so that's just the unfortunate reality of it. I wish it were different. Like, I wish that we had all developed languages that were very performant by default and whose libraries were very, that's just unfortunately not true. So that thing that you keep saying where it's like, oh, it turns out this wasn't very fast. We're going to see that a lot, unfortunately. That's just, okay.
I need to show you something. I need to let me just briefly show you where is it? Let me just show you something. Right, there we go. So the very idiomatic Java solution, which I wrote, which I talked about at the beginning of the stream, you essentially have these 10 files, 10 lines or whatever, and that does the trick. And that takes multiple minutes to run through.
Yeah, that's what I'm saying. It's a real problem, because basically what we teach people to do, because we're like, here is how you should program this, right? Is almost always very wrong. And people unfortunately get in their heads that well, that's still better because it was more about saving us time to implement things or whatever. And I don't necessarily disagree with that, but what I do disagree with is the idea that we don't need to then fix it. Yes, it may be nice to be able to write things this way, but then someone has to do the work to figure out how we're going to get that to run at least 10 times, if not more, faster, because it's clearly dramatically underutilizing your users' machines, and that's not really acceptable kind of thing to ship. So anyway, so yes, we're going to be seeing this probably a lot as we go through this. And you said it here, we probably need a custom double parser. We're probably going to need a custom hash map. Why? Because that's just unfortunately the state of programming today, right? That shouldn't be the case. That's just what happens.
What I would actually say is maybe we could come to some sort of a homework section for me at this point in time, because we've seen what I've done so far, kind of. And would you have anything in mind what I should try and tackle next?
So I need one more piece of information, because we didn't quite finish, which is each one of your threads is running this hash map, right?
Yep.
So they're getting merged somewhere?
At the moment, they're not getting merged anywhere. So this is they should ideally they should be merged at the end at some point. But at the moment, nothing's happening.
Okay. So yeah, I think one of the things that we're going to have to do next is we probably need to interrogate, before we do anything else, what I'd like to do is say, okay, we got sort of a not very complicated and a more complicated piece of this. The not complicated piece is we got to pull these bytes into memory. You said it was a 13 gigabyte file. Right? Yep. The more complicated piece is we have to extract the individual city names, extract the doubles, turn those, sum them on each thread, and then merge the thing at the end. Let's focus on the simpler part first, just because I think it'll be a good thing for us to start with, and that is we need to establish a baseline. One of the things that I talk about a lot of times in the course, and this is 100% the correct approach to optimization of any kind, is we need to establish what should the speed be for pulling in that 13 gigabyte file or whatever it is, right? So what I would like you to do is try to figure that out. Go do a couple tests. Number one, let's take a look, for example, at what is the speed of the speed of SSD, right? On the computer you're running this on. Like, what's it listed as being able to deliver for read performance at maximum, right? Because we might look and you might find that, like, oh, to read 13 gigabytes on this machine is 4 seconds. Then that takes that out of the equation for us, because we're never going to get any faster. So really then all we're worried about is, like, are we keeping things in the cache properly as they flow through to the next section or something like that? But we don't need to care anymore at that point about that 4 seconds. If it turns out that this machine is just some incredible SSD array, it's like it should be pulling that in a half a second or something, then we should be very worried because we're taking, quite a bit longer than that, right?
Good point.
So try to do that, and then also maybe try to construct a test in Java, play around with that a little bit to see what is the fastest you can get it to read in Java if the SSD speed indicates that the maximum possible throughput is significantly better than 4 seconds. That's what I would say for next time.
Okay.
Just to get us started.
Only that. So you can also give me extra homework. I mean, I'm happy to.
Well, the problem is we're going to be limited by what we can talk about in an hour every week or whatever, right?
Yep,
and so we don't want to do too much, because then we'll have too much to discuss. So I'd say let's start with that.
Okay.
Because then that's, especially if it turns out that there are faster ways for you to read this in Java, then we're going to have to think about some ways in which that might affect the design of the program as well, right? So we kind of need to know this going into it, because at the limit, we can optimize the heck out of that, parsing and merging and all that stuff. We can think a lot about how to get the CPU to do that.
Right.
We're always going to be bottlenecked on that baseline at a maximum. We will never be able to parse this file faster than it can be fed in. And if you want to add a 1C there, because this is a performance challenge, not just, we're not just optimizing this thing, but we'd take different approaches, right? For a challenge, there's some things we'll do in a challenge that we wouldn't necessarily do in production, right? Because we're thinking about trying to absolutely maximize something. What do we need to know about the machine this challenge is going to be run on? What's its SSD speed? How fast can it pull a 13 billion file out? See if you can figure that out, because that may also affect our thinking. Do we need to think about this other machine? Is it faster? Is it going to be pulling out of the file system's cache? Does it have, 64 gigabytes of memory? And are they running this challenge repeatedly so that we would get the benefit of it just pulling it out of memory instead of off of the SSD to begin with, at which point the bandwidth goes up substantially, right? Whereas on your laptop, is it going to devote 13 gigabytes to having stored this giant file for us in multiple runs? I don't know. So that's another thing that you could investigate. So I think there's plenty there for a week and plenty there for us to talk about. And maybe you could, as part of next week, maybe you could present to me also the specs of your laptop. How much memory does it have? What operating system is it running? What SSD is it using? And so that we can kind of just have an idea of what we can expect on your machine versus what we can expect on the challenge machine.
By the way, it sounds good. Okay. When you said what's the fastest way to get it to read it in Java, does that mean I need to have a benchmark with just, let's say, a single thread reading in the file and that's it, reading through all the bytes and just measuring that? Or would you then also already split it up and see by threads? And so
this is going to be driven off of that baseline number. What I really mean by that 1A, in other words, if I had to state this as homework, it is go find out how fast your SSD should be at peak and then get me as close to that peak as you can. That may mean using multiple threads, right? And again, also, and like I said, I'm sorry to dump all this stuff on you. This is why I say it's more than enough homework for a week. We have to know whether we're expected to read out of the file system's cache as well. We didn't talk about that, but when you read files, the operating system will cache those reads in memory opportunistically, right? And we don't really know because, like I said, there's so many different, in your head, you just kind of have to keep in mind this is a whole system. It's working and doing things. You have to kind of have a model of it. And what I'm thinking is, okay, for this challenge, someone needs to go find out by going and looking at the challenge specifications and how they are running it. Are we going to be running in a scenario where we can expect it to be cold loading, meaning we're getting these off of an SSD without them having been transited through a file cache where they might be warm? Or are we running them in this situation where they might be hot? So they're just going to run this like in a loop and take our best time, at which case, if this machine has a lot of RAM, it may decide to cache that whole thing. And then we're running at RAM speeds. Those can be 10x the speed of the SSD potentially. And then we're doing a very different calculus. And we're thinking of trying to hit a very different high throughput rate at that point, right? So again, all of that stuff is stuff I'm already thinking about because that is the only way we can establish our baseline. What is the fastest we could possibly do? And then from there, what we're going to do is try not to lose that baseline. In every step of the program, we're going to try to not fall off of it. And again, just to underscore this, because it's very important, this is the correct approach to performance-aware programming, or in this case, we're actually doing optimization. Like, we're going to be trying to get everything out of this, right? The reason it's the correct approach is because when people do the other thing, which is, I don't know, I timed it, I changed something, and I saw if it got faster, that doesn't tell us anything, right? That doesn't tell us if there's a whole missing swath of performance that we just haven't figured out how to get to yet. So what we need is we need to look at how fast the machine should operate and then see how much off of that we are, because then that tells us the things we don't know. It's like, what are the things we're not thinking to try? And it forces us forward in places where we might have just stopped and said, oh, I guess that's the fastest it could be, and walk away, right? We don't want to do that. So establish that baseline and then see how close you get to that baseline in Java. That's the first step we need to do, and we can forget about all the rest of the computation, because until we've got that down, we don't even know what our target is. Make sense?
Awesome. It makes absolute sense, and I just have to do the homework.
Awesome. Well, you know what? I look forward to talking to you after the homework then.
Casey, thank you. I really enjoyed the session. And,
me too. Thank you so much for having me on.
Yeah, we're going to see all of you again, hopefully next week or the week after.
Sounds great. Good luck, Marco.
Take care, folks. Bye.